Hello, this is Diego Apellaniz, and in this video we're going to take a look into some Grasshopper components that I developed to extend the functionalities of the Karamba 3D plugin, and we will focus on how to calculate the lifecycle assessment of a Karamba model so that we can optimize our structural system in order to minimize its carbon footprint. So let's get started. In order to install the plugin, you just have to come to my GitHub repository. You can find a link on the description of this video. And here, basically, you just need to come to releases on the right side. And you just can download the plugin through this link here. Okay, so once the download is complete, what you need to do is to extract the plugin files, but this is important, not into the Grasshopper components folder, but into the Karamba installation folder, right? And then I would just need to extract these two files. I've already done it. And of course, it's also important to check that they are not being blocked by your computer, right? So check that, and then once the files are already here, you can start Rhino. And when you start Grasshopper, in the tab of Karamba, of course, you should be able to see the new components folder of this Karamba package, right? Which are these three ones. Okay, and now let's go through the three examples of this plugin. And of course, we'll be extending ourselves a bit longer in the last example about lifecycle analysis. So let's go for it. And let's start with the load combinations example, right? So here, this example, this is basically a normal truss structure, but what it's important, it's not the Karamba model itself, but this component here, right? The load combinations component, which is the one that you can find in the new tab of the Karamba package. Okay, so basically the idea is that we have built our Karamba model, right? But the thing is that we can just provide individual load cases. In this case, of course, self-weight and so on and so forth. But the thing is that these are individual load cases, and of course, we might want to combine them into load combinations. So, of course, you can do it manually with all Grasshopper options and so on and so forth. But I created this new component in order to do these combinations of load cases in an automatic way. So basically, what we need to do is to plug the Karamba model in this first input parameter, and the second input parameter is expecting a list of load combinations, which you can see here in this Grasshopper panel. And well, you can define this list manually, but basically my idea was that you could define these load combinations with a commercial program. In this case, I did it with RFM, right? So this is a commercial finite element program. And here you can see the list of load combinations, and which is of course automatically created by the program, and you can export it into Excel and then import it into a Grasshopper panel like that. So you connect this panel with this component, and the load combinations are created. So basically, this output model has new load cases, which are actually the load combinations resulting by adding these load cases as specified here. Okay, so let's move on to the next example. And here it is more or less similar, but in this case we are going to focus on dynamic analysis, right? So here I have another structural model defined, which is this sort of building. But of course, the focus is not on this model itself, but how we are going to analyze it. So I created the model. This is a normal Karamba model, nothing very special here. But the thing is that if we want to, let's say, run a dynamic analysis with Karamba and analyze the natural vibration modes, for instance, we have, of course, to plug the Karamba model here. But you cannot specify the mass source, which is very important, of course, in order to calculate the natural frequencies and so on and so forth. So Karamba by default is always going to take the self-weight, right? But with this new component, which of course you can find again into this new tab of this Karamba package plugin, with this new component, it is possible to specify a load combination, right, in a similar way as we saw in the previous example, in order to add different load cases into this mass source that is going to be taken into account with the natural vibrations calculation. So that was it. Again, not very fancy, but it can be very helpful, I think, when it comes to dynamic analysis of Karamba models. Okay, so let's go for the final example, which will show how to calculate the carbon footprint of a structural system through a life cycle analysis out of a Karamba model. So let's go for it. And in this case, we have to open both the Rhino model and the Grasshopper model. So let's do that. And that's right, but I'm not going to open the final example, but an empty one, more or less. There we go. So here, basically, what we have is this. We have this structural system, which, yeah, let's say this is the slab system of an office building, and it's made up of timber materials, right? So we can see that we have a slab supported by beams, and the slab is cross-laminated timber, and the beams are laminated veneer lumber, right? Two different kinds of timber materials. And this is how the Karamba definition looks like. So basically, we have defined our materials right at the beginning, and it's important that we assign a name to them in order to know later on which one belongs to which element. And this is nothing special. So here, of course, we have the analysis of our model in order to calculate displacements, forces, and so on and so forth. And now this component of the Karamba package, which what this does is this, right? So we have to connect a Karamba model here, just like that. Actually, a calculated Karamba model could be a better idea. And what this component does is to break down all elements of our Karamba model into different materials, right? So this first output parameter, it outputs just all the materials that are assigned into different elements of our model. And now the other parameters are the interesting ones, right? Because what they do is basically to output the masses and volumes and even geometries of the different Karamba elements. And you can see that they have a tree structure, right? So that these elements are grouped by materials. So you can see that the first branch, all these 10 elements are my columns of cross-laminated timber, right? And so on and so forth. So here we get the masses in kilos. Then we can also get the volume of our elements in cubic meters. And finally, we can also even get the geometry of our Karamba elements as meshes, right? As we can see here. Okay, perfect. Actually, if we connect not the model coming out of this analysis component, but the model which comes out of the let's say cell view component, this one, we will be using the deformed geometry, which might be very interesting, as you will see later, right? I've just connected the output of the cell view component, right, with my life cycle analysis component. Okay, perfect. So okay, so this was all the whole functionality of this Karamba component, and until here comes the Karamba definition, right? And now I will show you a very simple example how to run a lifecycle analysis out of starting off with this new Karamba component. And for that, there are several Grasshopper plugins for lifecycle analysis, but I think the best one by far is the plugin of OneClick LCA. So this is the one that I am going to use. You can find a link in the description of this video where to download it. So you can do it. And now let's define our lifecycle analysis inside of Grasshopper, right? The first step with this plugin for OneClick LCA would be to define my LCA profiles. And of course, in relation to the materials that we assigned to our Karamba model. So first, let's start with our cross-laminated timber columns. And for that, of course, I need to use this component, LCA profile. And I'm going to use the filter material to navigate the database and find my material faster, right? Because there are more than 10,000 materials here in this database of OneClick LCA. So that's the purpose for these filters here. So let's select first the filter for cross-laminated timber materials. And for my columns, I mean, let's do it very simplified, but let's go for this material, right? CLT for structural elements such as beams. Actually, the next one was a better idea. For columns, pillars, and so on and so forth. So this is the first one. Let's move on. Now laminated veneer lumber, and again we can also use a search string for navigating the database, right? Besides of these filters, we have also these options. And actually we can see that there are not so many LVL materials, and this is because we are using the filter generic by default. So in this case, if we use manufacturer, we can see more materials, and for instance, let's use this one for my LVL beams, right? So the two materials are ready, and now let's go for the concrete. So the concrete, again, in this case, we can use the filters to find our materials faster. And in this case, we have this data source OneClick LCA, which offers, let's say, basic materials. So let's select concrete C35, and there you go. Okay, and finally, we need, actually, let's leave this here. And now, finally, or almost finally, we could need a material for our cross-laminated timber slab. So again, let's go for it. Let's select actually, again, a material filter, cross-laminated timber, there you are, and solid timber panels, for instance, perfect. So it seems like we are done, but we also need to define a material for the steel reinforcement of my concrete walls, right? Because we need to calculate the carbon footprint, which comes from all construction materials, and the reinforcement, the steel reinforcement is one of them, which we cannot ignore. So let's repeat this one last time, and in this case I'm going to go to the material category, reinforcement for concrete. There we go. Okay, so and the LCA profile will be rebar hot rolled. Okay, so now we are done defining my LCA profiles, and the next step within this plugin for OneClick LCA would be to define our materials, which are basically these LCA profiles with a certain quantity attached to them. So this is my LCA profile, and you can see that when I connect it to the component, this drop-down menu for the units gets populated with the available units for this particular LCA resource. So in this case, I'm going to select the option cubic meters, and here, in order to specify the quantity, there are two options. We can either get the quantity automatically from Briner geometry, right, a closed volume, and we could use that, or we can also specify an explicit quantity, right? So in this case, I'm going to get that explicit quantity from my volumes here, and in this case, of course, this would be the first branch, like that. The thing is that these geometries that we are getting here, as we saw, they are deformed geometries, so they would not be very accurate for calculating our quantities. But what we can do, though, is to use these meshes, right, these geometries. We can connect them here, and then we will use them later on to get our results for visualization in Grasshopper, right? We are not using them in this case for calculating the material quantity, because we are specifying it explicitly, but we can also use them optionally to visualize our results later on. Okay, so these were my columns, right? And now let's move on with the LVL beams. So I connect them here, and this it could be, of course, cubic meters again, and let's get my volume here, and let's get my geometry. There we go. And let's move on with my cross-laminated timber slab, and please take care that this is the branch number 3, so I mean the last branch. So this would be my first. Let me connect the profile here, and let's select cubic meters, and let's go for it. So that should be it, that should be it, and perfect. And now let's go for the final material, our reinforced concrete. So first, the concrete, again, cubic meters, and this comes from here, and also the geometry for visualizing the results. And finally, we have our steel reinforcement, but this is not explicitly modeled into Rhino, right? So what we are going to do for calculating this quantity is to assume a ratio of, let's say, 200 kilos per cubic meter, and basically using the multiplication component is how we are going to do it. So let's get the volume from the branch number 2, this one, and let's multiply these volumes by 200. Of course, you can do this calculation more precisely to calculate the amount of steel reinforcement into your concrete elements, but I'm going to do it this way. So this is my material, this is my LCA profile, and this is my quantity, and there is no geometry for my reinforcement steel. Okay, so that was it. All our materials are already defined. The next step would be to create our constructions, right? So constructions are here material, but with a class assigned to them. So first the columns would belong to the class column, and then the beams would belong to the class slab, and then the slab would also belong to the class slab, but of course I can use the same component because it's the same class. And let's move on with our walls. So my walls would be, of course, internal walls, and the steel reinforcement comes here as well. But now this is interesting because we have this group parameter here, and what this does is that when we have different materials but they belong to the same structural object, in this case concrete and steel reinforcement, we can group them, right, with a Boolean parameter. And now when we get the results of my life cycle assessment, the carbon footprint, we will get one result for both materials, right? Because it's the same structural element. And that's the reason for this input, for this group input parameter. In this case, we are also combining my beams and slab in the same construction parameter, but since they are different structural elements, I am not going to use the group parameter. And the next step would be finally to run our life cycle analysis. So let's get this component here, and we just need to connect the constructions, and there you go, there you go, and there you go. It doesn't matter if this is a tree. And here, this is very interesting because we have two different possibilities for running our life cycle analysis. First, before doing that, make sure that you have an account in the website of OneClick LCA. So you have to come here, OneClick LCA, and you should create an account here, right? Login or create an account. And basically, if you have like a normal account or a free account, you should be able to run the calculation in their website, right? And also in this plugin, there's the possibility to import the results back into Grasshopper, which is what we are going to do later on. But for that, you need an expert license, right? So first, let's assume that you don't have an expert license. And for that, we need to set this cloud parameter to true. And we also need, of course, to set the run parameter to true. So when this happens, you can see that a new tab is automatically started in the browser, and it brings us here to OneClick LCA, and our material quantities are imported here, and we just need to select the project in which we want to import these quantities. Okay, so let's select this project, let's select this design, continue, overwrite yes, and this is actually very fast, very straightforward. And now you can see that I have imported my materials, and this is the result of my life cycle assessment. I have my results in kilos CO2, of course, and regarding different phases of the lifecycle assessment. And I have even very interesting graphic shapes here for understanding my results better. Okay, I'm not going to spend a lot of time here, but again, if you come to this option, construction materials, you can see the materials that we have just imported, my concrete and marble reinforcement and my timber materials, right? Both from the slab and from my beams. And here are my columns, right? They are broken down into different classes. Okay, so that was it, and these are my results. This was, I think, actually very fast and very straightforward. And let's leave it like that. But again, I encourage you to spend more time here in this website of OneClick LCA to see the different options and possibilities to analyze these results, and so on and so forth. Yes, and of course you can also get different benchmarks and graphs and so on and so forth. But let's stop right there. And now let's take a look to the other option, which is not to run the analysis in the cloud, but to get the results in Grasshopper, right? And for that, what you need to do first is to log in. In this case, I already did, but if it's the first time that you are using of course the plugin in this Grasshopper session, you should need to log in. So for that, you just need to connect a button here. Click on the button, and then this pop-up window should appear, and you just need to paste your username and password here in this field, so like that. Okay, and again, remember that you need an expert license to get the results back into Grasshopper, otherwise you won't get any result. And that's right, so this is the carbon footprint of my structural system, in this case 60,000 kilos CO2 equivalent. But this is not the only thing that we can do, but also, as we previously announced, we can also visualize the results of my lifecycle assessment. And for that, we need this last component, visualize results. And we just need to connect my constructions here. So there you go, and there you go. So this would be the results of my lifecycle assessment. First, I'm just going to point out that this component is very interesting for checking the results. In this case, I can see that I'm just importing one of the walls. I'm just getting one wall because we should combine in a Grasshopper fashion, right? So this could be my first branch, and this would be my second branch. And now, in order to combine these materials, we need, of course, list. In this case, we are going to combine each time two materials, right? Concrete and steel reinforcement for its walls. So this is what we need, lists of 2 elements each one. So let's connect this here, and now you can see that the results are updated, and here I have all my walls. Okay, perfect. So let's get back to my visualize results component. And here we have different options. We can either show the results numerically. So for instance, result absolute, and here you can see all my results. And again, you can also filter your classes. These are my columns, and these are my walls, and these are my slab. Of course, this is my slab. And also, you can actually use the color options as well, right? Which might be interesting for different options. So results by volume, results share, of course, these columns could be like 0.3, and probably the slab is taking the highest amount of CO2. But in order to see which materials are contributing the most, these options are very interesting, right? Quintile absolute share. There you go, and in this case, now you can see how the columns, of course, get the number 5 because they have, let's say, a relatively low mass in relation to the other structural elements, and the walls could get the number 1 since they are responsible for the highest impact here in my model. So that should be it. And also you can also check your resources. So you can see, for instance, okay, so, and yeah, perhaps for the beams it's not very clear here, but the reason for that is that we needed to divide these beams into several elements for the Karamba model, right? So this is not a problem for the plugin of OneClick LCA, but this is a requirement from our Karamba element. So if we leave the beams, actually, let's filter by internal wall. Here you can see that we can differentiate our materials. Our materials are two materials that are attached to this wall, right? The first material is concrete and the second one is my river. So this is another way to check that we are calculating our analysis properly, right? So that should be it. That should be it. Okay, so this is how we can visualize the results. Let's hide the numeric values here. And also one thing that you can do is to optimize your structural system in terms of carbon footprint. And this is something that we explained in our paper, this one that we presented in the CMOUT conference. I will leave a link in the description of this video if you want to take a look into it. But basically, there are different workflows with many other plugins. In this case, we're presenting optimizations workflows with Karamba, Octopus, and of course the Parametric finite element toolbox. But there are many different workflows possible. So take a look into the paper if you are interested. And now I'm going to show you how to use Karamba and Galapagos to optimize or to minimize, better say, the carbon footprint of our structural system. So this is the parameter basically that we need to minimize. But of course the thing is that the most optimal structure would be the structure in which with the lowest amount of material, right? But this would be if we were talking about the structures with just one kind of material. In this case, we have a structural system for our slab, which is made up of a slab and beam elements with different materials. So we need to find the right dimensions for both beam and slab elements that lead to the minimal carbon footprint. So I could be playing with the dimensions of my beams and my slab, right? So let's define the optimization loop with Galapagos. There you go. And that's right. So let's start with the input parameters. And I was saying that they were going to be the dimensions of my slab, of course. There you go. And my beams. Where are my beams? Here they are. Okay. Okay, so these are my press and hold the shift key, of course, to select two different input parameters. There you go. And now I need to define my fitness function. So of course, what I want to minimize is the carbon footprint, but I have to take care that I don't define my structural elements so thin that the structure doesn't work anymore. So what I'm going to do is to define a fitness function which will penalize the solutions with excessive deflection. So what I'm going to do is to get the larger than component to check the deflections that are above a certain value. In this case, let's assume that we have a limitation of 1 centimeter, right? So this is a simplified example. You can do it as complex as you want. So I'm getting my displacement here, and I'm going to check that they are not greater than 1 centimeter, right? And the output of this parameter is centimeters again. So let's check that, and in that case, if this is true, what we are going to do is to add a very high value to this carbon footprint. So this is what we are going to do. And if this is true, so we should use like a stream filter probably. And this is my, that's right. And if this is 0, I'm going to, so if this is false, right? If the deformations are more or less okay, this is going to be 0. And if the deformations are very big, let's get a value, I don't know, for instance, 1 million, right? So that Galapagos in this optimization loop sees that these solutions are not valid, right? So that should be it, and this is my fitness function actually. And let's do let's do a small test before starting Galapagos. So if I come back to the beginning, and let's say I set my slab to be 10 centimeters, and actually, and my beams should be even lower. Then in this case, that's right. In this case, we can see that the deformation is very big, and we get our carbon footprint penalized, right, by this value. So again, Galapagos should be the responsible for finding the optimal dimensions for my beams and my slab so that we minimize the carbon footprint, but still the structural performance is acceptable. So this is my fitness function. Let's connect it to Galapagos here, and that should be pretty much it. So let's go for it. We just need to do double click into Galapagos. Let's leave this guy here, and this is Galapagos. Okay, so we'll double click. This is set to minimize, right, important. And yeah, I think let's go for it. Okay, so we can see that this value is not improving any longer, so I think we can stop our optimization at this point. And that's right, so now this should be the optimal value, 45,000 kilos of CO2 equivalent. That could be our carbon footprint. And this is coming from these dimensions, right? For actually from a slab, which is very thin, just 11 centimeters, and yeah, more or less deep beams with 80 centimeters. I think there are very interesting conclusions from these results. And you can, I'm not going to extend myself here, but you can take a look to our paper again if you want to see these conclusions, let's say in more depth, and also other possible workflows for optimizing our structural systems with other plugins such as Octopus, the Parametric finite element toolbox, and so on and so forth. So I'm going to stop this tutorial here. I hope it was interesting, and hopefully you will start calculating the carbon footprint of your structural systems. And yes, good luck, and yeah, let me know how it goes.